First problem set will be posted on the web tomorrow, and I will alert you to that with email. As mentioned, just to remind you, I will have office hours on Mondays. At noon to 1 in room 30, okay? And we'll start our problem sessions currently scheduled in room 5 until further notice on Wednesdays. What is it, at 12:30? I forget when we start. So it's 12:30 to 1:45. Okay, so I just wanted to correct some errors from last lecture. In fact, in just doing so, I see that in fact, unfortunately, my notes still have an error in them, and I need to correct that. It has to do with the difference in the way Jackson conventions work and the way that I had thought about them in the past, and that's why things got a little bit confused, but I think this is right. So, not that this matters that much. All these details of all these K1, K2s, and alphas, we never use them. Okay? It's just I wanted to show you what the sort of general principles are, and then the specific cases that we work with. The point here is that we need to define some conventions for the units, and the whole point is that when we deal with electricity and magnetism, we have a new quantity, charge, and somehow the units of charge need to be related to the units of force, somehow, okay? And that's the whole story. And so the conventions are based on the empirical laws of electrostatics and magnetostatics, the Biot-Savart law and the Coulomb law. And so there are constants here that convert current to force and charge to force. Of course, current is just charge unit time, so that's the deal. One thing we noted, and I had this reciprocal in when I wrote it last lecture, that the units of whatever these constants are, their ratio is related to a velocity squared. Okay, that's just because we have here current is charge unit time, so length unit time, so we have a velocity here and another velocity here if both of these are going to be forces. And that turns out empirically to be that velocity is nothing other than the speed of light, which is already a hint about the relationship between light and electricity and magnetism. Quite a profound hint, in fact. And as we discussed, these forces can be reinterpreted as the local action of a field on a charge or a current. And so we get definitions of electric field and magnetic field. Now, one of the things I realize is still wrong in my notes, and I will correct, to be consistent with the notation in Jackson, is how this additional constant alpha is defined. I had it reciprocal in the notes last time, which is one of the reasons all things got confused, and I apologize for that. The point of this extra constant is that we have, in some sense, freedom. We don't have to define the electric field and the magnetic field to have the same units. Okay, so that's the third constant that appears here. So written in terms of these constants, this is a question Brad asked at the end of lecture last time. We could write Maxwell's equations in a general form in terms of these three conversion factors, K1, K2, and alpha. Once we constrain K1 and K2 to go into the speed of light, it's really two constants. And the two sets of units that are most common are the, perhaps most familiar to you, the SI units, in which K1 and K2 are defined in terms of the epsilon naught and U naught permittivity and permeability of free space, so-called, with alpha being 1. And the units that we will use in this course, which are the Gaussian units, in which K1 is set to be equal to 1. So that Coulomb's law just is the product of the charges divided by the distance squared, and K2 then must be 1 over c squared. And so the force actually is 1 over c squared times this. I had it as 1 over c, so that should be corrected as well. Yes?
What are the units on charge then? Do they change?
They are different. So it's not a Coulomb.
Yeah.
It's called an ESU. And it's related to the Coulomb through the speed of light. So if you actually wanted, so it's a good question, what the heck if I actually want to get a number out of this thing? Well, you know, that's kind of depends. We'll see some problems. Ultimately, you have to either use the consistent set of units, and so if the charges are given in coulombs, you have to look that up. How is a Coulomb related to an ESU? Most often, when I'm working with these kinds of things, I mean, in electrostatics, it's not the most convenient thing to use Gaussian units. It really isn't. I mean, practically, you know, we want to talk about volts. We don't want to talk about stat volts, which is 300 volts, right? I mean, I can convert these things because I'm old enough to remember what these things are related. However, quite often, what happens, as I mentioned last lecture, when one is dealing with physics problems, typically what we do, and the most important thing to do, is to first think about what are the scales in the problem, and factor out the characteristic units so that everything is dimensionless and then defined in terms of some characteristic units. So I'm working in atomic physics. There are so-called atomic units. So you relate everything to the Bohr radius and the Rydberg energy and so forth and so on. And then those things are kind of constants and you convert them. We'll have practice doing that. But they are different units. They are different numbers. Okay. All right, I will make this alpha correction in my notes. Onwards. This won't be the first time the notes have mistakes in them. Such is life. So, in order to deal with the analysis of electricity and magnetism, obviously we're going to be dealing a lot with vector calculus, and we need to kind of refresh some memory about that. And moreover, a very important concept that we will play on throughout the semester is the notion of vectors and tensors. And so what I want to spend today doing is establishing a bit of a baseline for talking about vectors and tensors. Some of what I'll talk about is quite trivial stuff that you know, but I want to establish a kind of notation and some of the basic concepts that we're going to build on, not just in talking about the phenomena of electricity and magnetism, but what they ultimately lead to in thinking about special relativity, which hopefully will be the crowning point of our semester, and having some foundation in vector and tensor spaces will be important for discussing special relativity as well. All right, so let me begin by motivating this by just talking about Euclidean space. And this, of course, we have comes by thinking about three-dimensional physical space. So we have our three-dimensional space here. And we have the position in three-dimensional space denoted here as x. And that has some representation in terms of a basis. So we have basis vectors. I'll call E1, E2, and E3. They're unit vectors. And as we will thus define, because this is a basis, we can expand our position in terms of these basis vectors with coordinates x1, x2, and x3. So the notation I will use is if I'm talking about the representation of the vector with respect to the basis that is chosen, in this case, then I'll write as a column vector with this little tilde underneath to say it's a vector, but it's the representation of this vector with respect to the basis. Okay? Right. Okay. In addition, to remind you, we will introduce here the Einstein summation convention. Which is, yes?
If we're using the Einstein summation convention, shouldn't one of those i's be a superscript?
When we want to make a distinction between, when we have non-Euclidean space, and we will get to that, and we have the notion of the dual vectors, and we have notions of the covariant and contravariant vectors, then we have to be very careful about when we're talking about superscripts or subscripts. But when we're talking about Cartesian space, there's no difference between them. Okay, so there's no reason to carry around superscripts and subscripts. We'll get to that later. But at this stage, there's no geometric difference between so-called covariant vectors and contravariant vectors. And we're getting way ahead of ourselves. We'll get to all that stuff at some point. But the convention here, which is just fine, is that we define the summation. I mean, this would be equal to I equals 1 to 3. X1, X2. I'm sorry, it should be I. Okay, that's what that means. Okay? So the Einstein summation convention, as you have learned, I hope, is useful in dealing with vector and tensors, which is to say, if we have an index which is repeated, then it is implicit that is summed over. So it's a shorthand that we use in order to not have to write out sums. Okay, and it's quite convenient. We'll see today some examples of that, of how that works, if you haven't played around with it before. All right, so given this, we also have, in three-dimensional space, we have the notion of the inner product, or dot product, which is one and the same as saying that there is a notion of length on the space, as I will remind you that these concepts are interrelated. So the dot product can be defined as, in one way of defining it, is what happens when I look at the dot product between two basis vectors that I define to be orthogonal, in fact, orthonormal. So given the definition on the basis vectors and the fact that the dot product is linear, meaning that if I look at the dot product of some position vector xa with a vector which is a superposition of two other through a linear combination. This is a vector space, so we can always take linear combinations. Then the dot product distributes through in a linear way, as you know. So, given that, if I look at the dot product of some position vector with itself, now I'm going to use the Einstein summation convention. So we said x vector was equal to the linear combination of the basis vectors weighted by the xi's. Now this is important when you're working with this notation. It's always important to remember what is summed over and what is a dummy index. In other words, if I just wrote this again as dot xi ei, I'm really confused because am I summing this with this or this with this? You cannot and should not reuse an index once you've summed over it. This is the notion, this index is sometimes called a dummy index. I mean, I sometimes am quite a dummy without my reciprocal, but this is the dummy index. Okay, meaning what? Means I can call it anything, you know. I'll call it smiley face. That's a good index. I mean, as long as it's the same index, it's fine. It's a dummy. It's already done. Okay, it's a stand-in. That's what we mean by it's a dummy index. So once you use a dummy index, it's gone. Don't use it again in the same equation. So I'll call this one J, or frowny face. All right? Very important technique for dealing with this kind of thing. So this then becomes xi, xj, ei dot ej. Now, of course, you remember this Kronecker delta is 0 if I not equal to j, and it's equal to 1 if I equal to j. That's what we mean by this symbol, as you know. So this dot product is equal to delta ij. And now we have this sum where repeated indices are summed over. So I is summed over and j is summed over. And now the trick is, because the delta, the Kronecker delta is 0 unless I equals j, and when you sum over either I or j, this will be 0 unless the two indices are the same. So this becomes, if I sum over j, for example, then I'm left with the sum over I. Now this is a very pedantic way of writing something trivial that everyone knows, but just to show you how, it all comes out, because we'll get to more complicated examples in a moment. And of course this means the sum of x1 squared plus x2 squared plus x3 squared. Which is nothing more than the length of that position vector according to the Pythagoras theorem. So the existence of a dot product is one and the same to say that there is a notion of length. And this defines what we call the metric on the space. That is the way in which we relate length to the coordinates. In this case, it's a trivial metric, but we'll talk about more complicated metrics when we talk about relativity. Okay? Of course, we also have, from the law of cosines, that if I look at the dot product between two vectors, I can also express that in terms of the magnitude of the lengths times the cosine of the angle between the two vectors. All right. All right. Another important concept that we will talk about in some detail is thinking about a change of basis. So let's imagine we had our original Cartesian space. And let's say we do a change of basis, for example, that is a rotation to a new set basis where I've rotated, in this case, about the 3-axis by an angle theta. Okay? So I've just rotated and the new vectors are in the plane there, in the 1, 2 plane. So in this case, my new, I guess I'm not putting hats on it, but anyway, you'll excuse me, sometimes I'll put hats and sometimes I'll forget that they're unit vectors. This vector, just from geometry, is cosine theta E1 plus sine theta E2. The new E2 prime, has a negative component minus sine theta E1 plus cosine theta E2. And I left in this particular, as in a particular example, I just left those alone. And we could write this as a matrix equation where the new basis vectors are related to the old basis vectors through this matrix, okay? Which I'll call R. So the set of new basis vectors, the ith basis vector, is related to, in the new coordinate system, is related to the basis vector in the old coordinate system through this matrix equation, sum over J. So matrix multiplication in the Einstein summation convention, I'm summing the row with the column, right? So this is a shorthand for this, where these matrix elements are row column, sum over J. You should always check that there is an index that on the one side of the equation is equal to, so this is not a dummy index, this is my fixed index. So on the left-hand side of the equation here, I was the particular index I chose to call this. Whatever I sum over on this equation, at the end of the day, I better have that index I left. All right? Okay. Right. So, stick over here. Now, the particular rotation I chose, this particular change of basis that I'm looking at here is one that kept the dot product or inner product between these vectors the same. So in this case, here R preserves the inner product. So what that means is that the new basis vectors must remain orthonormal. That, as you know, puts a constraint on the nature of the transformation matrix. So let's write that out. So I got I and J. I and J are fixed indices. I can't use those letters again because they're fixed. If I want to introduce a dummy index, I don't want to use I and J. So there's K and L. So EI prime is equal to I R I K E K. Okay? Okay. I K. Something K. Dotted into the jth index R J L E L. Is that clear how I dealt with dummy indices versus fixed indices? It's really important. You're going to get lost. Your equations are going to be messed up if you don't pay attention to what's a dummy index and what's a fixed index. Once again, we have, this is a linear operation, so the dot product comes through. Remember, these things are numbers, so I can put them any place I want, even though they're the elements of a matrix. And matrices don't commute. The matrix elements, which is what these things are just numbers, and I can put them in any order I like. R-I-K, R-J-L, E-K, dot into E-L. which is delta KL. Now I can sum over L, and since that means replace every L by a K, according to the lovely Dirac symbol. And thus, and this is supposed to equal, so what I learned from this is that R I K times R J sum over K is delta I K. And we can re-express that as a matrix equation. Now remember, when I multiply matrices, I have to sum the rows with the columns, right? So this isn't written in a very convenient form. Let me just do a little aside over here. If I have two matrices, A and B, and I want to look at the ijth matrix element of that, you remember that is, well, I have to sum the row with the column, right? So this is not written as matrix multiplication yet, because I'm summing a row with a row, or I mean a column with a column. I mean, actually, I should be doing it. This is row, column, row. Everyone said yeah, but say no. Okay. In order to do that, I need to switch rows and columns, which is equivalent to which is the operation of taking the transpose of the matrix. So I can look at this just to be more clear. This is the ikth column of that matrix times the kj element of the transpose of the matrix. When you take the transpose, you switch the row and the column, which means switching these two indices. So this is equal to R times R transpose ij. When we sum over K, that's taking multiple matrix multiplication, and that equals delta ij. So what we learn here as a matrix, remember the matrix whose elements are 0 unless I equals j is nothing more than the identity matrix. And thus, what we remind ourselves is that a transformation on the space of change of basis which preserves the inner product, that transformation matrix R must satisfy R times R transpose is equal to the identity. Or equivalently, what this says is that the inverse transformation is equal to the transpose. And matrices that have that property are called orthogonal matrices. So the matrix transformation, if it preserves the inner product of Cartesian space, then it must be an orthogonal matrix. An orthogonal matrix is one whose inverse is equal to its transpose. You might remember if I had a complex vector space, like in Hilbert space, then those are unitary matrices, because I have to take not only the transpose, but the conjugate, which is the adjunct. So, just a little aside there. All right, So, very good. Now, we're going to come to one of the issues that was raised about the question of upper and lower indices. So the way I've defined my transformation so far is, well, I did something to the basis, right? I changed the basis, and just by using vector addition, I was able to relate the new basis vectors to the old basis vectors. Sometimes it's more convenient, and quite often it's more convenient to think about this as not a transformation on the basis vectors, but instead a transformation on the coordinates. So what happened here? Oh yeah, okay, good. Right, so do not trip Deutsch. All right, so the vector is the vector. We're not moving the vector. We're changing the coordinate system. So whatever, if the vector had an expansion in these basis vector, it's the same vector but with a new representation. Okay? I'm not rotating the vector, I'm rotating the basis, or rotating the coordinates. And we just said this was equal to RJK EK. All right? So, now, in principle here, the notion of W and Z again, I want to be clear. I could write this. I mean, let me write this out here. This is perfectly fine because this is summed over. This is summed over. It's not like they're in the same equation. So I'm going to do that so I can equate things better. Because now what I see here, oh, yicky. This is going to be, no, never mind. Let's go back. That was fine, but it's going to be hard to relate things. Let's. I'll do this. That's fine, because now xi is equal to xj prime sum over j, fixed index, findex index, all good. Okay, so now as written, this is a perfectly fine equation, but it's quite often useful to think about this as a matrix equation. So again, let me write a little aside. If I have a matrix times a vector, and I want to look at the new vector, then I can think about that as a matrix equation. Now that's not what I got here, because I'm sort of summing in the wrong direction. So what I want to rewrite this is equal to R transpose ij times xj prime. So we have the old coordinates are equal to the transpose of that matrix ij times the new coordinates. But that's not what we want. What we want is what are the new coordinates in terms of the old coordinates. So I have to take the inverse of this equation. So this is the general equation that relates if R is the transformation matrix on the basis vectors, then this is the transformation matrix on the coordinates. I know this is tedious beyond belief, but this is what we got to deal with. Now, in the context of Euclidean space, we just said that the transpose was equal to the inverse. So for Euclidean orthogonal transformations, then R is equal to, the transpose is equal to the inverse, so the transpose, the inverse of the transpose is back to R again. So in this case, it doesn't make a difference. This is equal to the same transformation matrix that transforms the basis vectors, also transforms the coordinates. But that's not true in Minkowski space. So the things that transform according to R are called covariant, and the things that transform according to the inverse transforms are contravariant. That's where those terms covariant and contravariant come from that we'll see in the semester. That's why I'm doing all this very tedious stuff, because we're going to need it. Okay, so the coordinates transform according to R. Thanks, Andy. All right, so far we've defined our vectors as what we know about position and three-dimensional space, and that gives us the general definition of a vector. Not just position, but any general object. We abstract it by saying that anything that has the same kind of transformations as position is a vector. So we define a general vector to be the linear combination weighted by whatever three numbers, they don't have to be position, by the same unit vectors. And it is a vector if and only if I change the basis the new coordinates of the vector are related to the old coordinates by the same transformation that we had for position. So for example, if I define momentum as mass times the derivative of position with respect to time, with these being scalars, then this has the property that we get of a vector, because it inherits it in some sense from position. Yes?
This seems non-general. What about a translation of the coordinate system rather than rotation?
That's just fine. That will be another example of a orthogonal transformation will preserve the inner product. I looked at this as an example, but as long as it preserves the inner product. In fact, it doesn't, we can do transformations that don't preserve the inner product, those are fine too. But then they won't satisfy, this will be the transpose inverse rather than, inverse transpose rather than R, only for orthogonal matrices.
The translation doesn't actually preserve the inner product of position vectors.
If
As long as you're just
translated.
talking about pure rotations,
Mhm.
then it actually preserves the inner product of position vectors, even though that by itself isn't physically that meaningful.
I mean, as long as we have a good group of transformations, I don't think it's, you know, whether whether or not we preserve the inner product is not important. It's just the particular case we're looking at the moment. All right, so we got vectors. Now, there's one last important point here in terms of Euclidean space, and that's the notion of handedness. So one thing to note here, if I look at what we have here for orthogonal transformations, we have that R times R transpose was the identity. Right? And if I take the determinant of each side of this equation, well, the determinant of a product is the product of the determinants. And the determinant of the transpose of a matrix is equal to the square, is equal to itself. So therefore, what I have is this is the square of the determinant is equal to the determinant of the identity, which is the product of its diagonal elements, which is 1. So an orthogonal transformation is one whose determinant squared is 1. And there's two choices. There's the determinant of R is 1, or the determinant of R is minus 1. And rotations satisfy this case. They're so-called proper rotations. And a transformation which does this is sometimes called improper, though it's perfectly allowed. What kind of transformation is one which preserves the inner product, but whose determinant is minus 1? Well, something which switches the handedness. So let's remind ourselves about that.
Reflected across an axis.
For example, indeed. So if I have a transformation which that takes, say, E1, E2, E3 to E1, E2 minus E3, right, that R is 1, 1, minus 1. And that is a reflection. So a reflection, not a rotation, is one, or some combination of reflection and rotation will be a transformation which changes the handedness. And what we mean by the handedness, as you know, is the famous right-hand rule, which is to say we define some convention here, because most of us are righties, that E1 and E2 have the handedness such that this is E3. All right? So this is a right-handed coordinate system. Make sure if you're a right-handed person that when you do the right-hand rule, you put down your pen. It's always, oh yeah, yeah. No. Not going to work. All right. So in dealing with the right-handed coordinate system, it's useful to introduce the cross product. So the cross product defines the handedness such that EI cross EJ is equal to plus or minus or 0 depending if I equals k. So we introduce the famed Levi-Chita symbol. Where epsilon ijk, oh, let me go to the front door. Right. So epsilon ijk is 0 if any two indices. Let's get some better shots here. Are equal. It's equal to 1 if I equals 1, j equals 2, and k equals 3, or cyclic permutation. Right, so that's I equals 3, 1, 2, or 2, 3, 1. Cyclically permuting. Okay? And it's equal to minus 1 for non-cyclic permutation. E.g., I equals 1, j equals 3, k equals 2, or 2, 1, 3, or 3, 2, 1. So, some important properties here. If I were to write out, there's a relationship between determinants and the anisymmetric epsilon ijk. So, of course, what this means is that epsilon ijk equals to minus epsilon ikj. If I flip any of the two indices, I get minus. Because of this non-cyclic permutation. So it's sometimes called the completely anisymmetric tensor. We'll get to tensors. So the determinant has the anisymmetric property. So if I look at epsilon ijk times a set of three numbers v sub I, let's see what I got here. Ui vk w or vj vwk ijk. We've summed over I, summed over j, summed over k. This is equal to the determinant of the matrix, with the entries being those three vectors. Right? Because if you switch any row or column, the determinant is minus itself. And if any of the two rows are equal, then this is also 0, you expect. Alrighty, so from that we recall the following relationship. If I look at a vector C, which is the cross product of two vectors, A and B, EI cross into that vector, use different dummies, then the cross product is also linear, so I can move this through BJ, EI cross EJ. And that we just said was equal to epsilon ijk ek. Using the relationship here. This is epsilon ijk ek. So, if I look at this, I can also rewrite it we've summed over all the indices. Let me rearrange them and call this epsilon ijk aj bk I using the cyclic property. Then this tells us that the kth component of C, or the ith component of C, that's C sub I, is epsilon ijk aj bk. So, in dealing with cross products, you could deal with determinants, but I never do. Because we'll play around with this long enough to know that what I have to do is introduce the Levitchivinus symbol as appropriate, and from that we can quickly deduce what we need to know about the cross product. So let's do an example here. So one last thing, I have to have one identity here that's extremely useful. Suppose I look at epsilon ijk times epsilon kln. Sum over k. So what's ever left depends on the fixed indices I, j, l, n. And this is equal to delta IL delta JM minus delta IM delta JL. So important, I remember it. You can check that for yourself. In the derivation is tedious and not interesting. Why do I care? Maybe I don't, maybe you know, who knows. But let's look at an example, how we use this notation for doing manipulation and analysis. Consider the vector triple product. Okay, so suppose I wanted to, needed to find out, wanted to simplify this, and I didn't remember back minus cab. Now you remember back minus cab. Let's see how that goes. So what I want to do is what is the ith component of this vector in terms of the components of these vectors? Well, what do we have? I have epsilon ijk aj times the kth component of this vector, right? Because that's what we just said, how I got the cross product. I take epsilon ijk, first thing, second thing. Now, I got to find the kth component of B cross C, which again is, well, let's just put that over here. That's epsilon K LM BL CM. Notice, don't use the same dummy index, use a new one. All right, so we got epsilon ijk, epsilon KLM, AJ, BL, CM. All right, so now here's this identity. Take this, plug in that. And what do we get? Well, in the first term, I have a delta IL, which means I replace L with I, and a delta JM, which means I replace M with J. So this is the first term, gives me DICJ, right? From that delta function, those two delta functions. Then I got this delta function, which says replace M with I, and J and L. So I have J, B, L becomes J, and M becomes I. Check. The left-hand side, the fixed index is I. Here, I sum over J, dummy, fixed. So it's all good, it's in here. Now, this is, how do I deal with this? Remember, these numbers can go in any order. So I can rewrite this as DI times AJCJ minus CI AJ BJ. And AJ CJ sum over J is nothing more than the dot product between A and C. And similarly, the sum over J is the dot product between A and B, which is equal to the ith component of A cross bed or chalk. So what we've learned from this is we just derived that A cross into B cross C is D times the dot product between A and C minus C times the dot product between A and B, or the famous back minus cab rule. So you're on a desert island. You don't have the inside cover of Griffiths. You're going to have to pass your prelims. What are you going to do? You're going to whip out your epsilon IKKs, and you're going to just go to town. All right. Continuing on here. So this is the kind of mathematics, notation, manipulation that you're going to have to get used to. And our first homework is going to be all about this. All right, last topic for today. So we talk about vectors. I want to talk now about tensors. Tensors are going to be an important part of the discussion this semester. Right. Okay. So to motivate that, by the way, what time is it actually? Okay, good. So let's think about rigid body motion. So let's imagine I have some rigid body, whatever it is, and it's rotating. Let's make it rotate the other way. Around some axis with angular velocity omega, rigidly, right? So that means that every point in this rigid body is rotating at the same angular velocity, okay? So the angular momentum of that body, well, I sum over all, let's say there's I'll just, so I should write it as an integral, but let me just write it as a sum because I don't want to deal with continuum for the moment. So there's the alpha position here. Each one, it's a little dm, but I'll just call it m alpha. So we have, r cross p, or position crossed into momentum. So this is not a coordinate, this is a particle index, or point in that rigid body. Right? R cross P is angular momentum, or x cross MV. So our velocity here is, good. Forget it, no wonder I don't have any big shock. Is equal to each, because it's a rigid body, each is moving around an angular velocity omega, so this is x cross omega. Yeah, omega cross x. make a crossover. Okay, and we just did our famous back minus cab rule. So this is equal to the sum over alpha. M's of alpha are alpha squared times omega. That's B A dot C, where R sub alpha is the dot product between these two, minus C A B. So C is X alpha. Yeah. AB. Okay, that's the triple cross product we just did. So, the point here that you see is that the angular momentum of this body is not necessarily in the same direction. Everyone's the same omega, pardon me. Is not in the same direction as the angular velocity. Because this vector summed over all these particles isn't necessarily in the same direction as omega. So the angular momentum of this thing is not necessarily in this direction. And the way we deal with that is to write this then not as a number times omega, but a tensor dotted into omega. And this tensor is the moment of inertia tensor. What is that tensor? Well, the way, if we look at it here, that tensor, written with the two, with this devilish double arrow on top, is equal to the sum over all the particles, m alpha r squared times the identity tensor, because when the identity dotted into omega, it gets back omega, minus x alpha, where this is not the inner product. What's left?
The outer product.
The outer product. So, this is what's called dyadic notation, where if I just write vectors next to one another, they become a tensor. What this means, stated another way, is if I look at the ith component of the angular momentum, I don't multiply, that's not just proportional to the ith component of the angular velocity, but instead is a matrix multiplication. And this matrix is what we call the moment of inertia tensor. And its components are here. Let's go to the next board. Meet me in camera 3. It says John Stewart. And back over here. I think my record is 3 times around, but. So, Ij is equal to sum over alpha and alpha r alpha delta ij. That's the ij component of the identity minus the I component of x alpha times the j component. Okay, so this is the outer product. When I take the outer product of 2 vectors, I got a matrix. Take the inner product between 2 vectors, I got a scalar. So, one of the things we see about this inherits the rotation, if I look at this in a new coordinate system, then I have to rotate each of these guys. So the new matrix in the new coordinate system, I have to first rotate this guy, then rotate the second guy. Because I need to perform transformation on this and transformation on that. So to transform a tensor, in this case, this is a rank 2 tensor. We must transform this with 2 rotation matrices, summed over the 2 indices associated with this rank 2 tensor. So let's conclude. Wild guess. If you have a rank n tensor, what would you do? Well, you'd have n of these guys. So if I had a rank n tensor, which has n, so I have an I1 index, an I2 index, dot, 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 up to the nth index. It's a rank n tensor. Then, in a new coordinate system, I'd have J1, J2. I have all the n indices is Ri1, J1, Ri2, J2, R blah, 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 up to Rin, Jn, T, I1, I2, dot, 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 In. J, I'm sorry, something J. Crop. I1, I2, dot, 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 In, J1, J2. Object which transforms this way is known as a rank n tensor. And we will see then. We will see monopole moments, dipole moments, quadrupole moments, octupole moments, hexapole moments. They're all higher order tensors. And they are very important in the theory of electricity and magnetism. All right. Anybody have any questions? We will pick this up. Notes are on the web. We'll review this next week. There's homework on this subject due a week from Friday.